Bon, tout d'abord, merci beaucoup pour l'invitation. J'ai ravi d'être ici et d'avoir cette occasion de présenter quelque chose pour vous. Et veuillez m'excuser pour présenter dans une autre langue que le français. So, let us begin with a little experiment. Construct the number 2 in your mind. Keep it in memory. And now construct the number 3. Add them and keep the results in your memory. Now construct the number 5 and compare it with the result of the sum that you just made. You will see that they are the same, so now you judge 2 plus 3 equals 5. Now, according to Brouwer, all mathematics is like this. He wrote, Intuitionistic mathematics is a mental construction. This term intuitionism is the name Brouwer gave to his philosophical brainchild, his account of mathematics, its ontology and its epistemology. The fundamental tenets of this account are the following 3. First, mathematics is a descriptive science. Second, what it describes are mental objects, objects constructed in the mind. And in particular, these objects do not have an independent existence in some Platonic realm, for example. And third, the human mind has access to these objects by reflection and introspection. The idea of an existence of mathematical entities outside of our minds is a metaphysical idea, and intuitionists do not want to let that idea enter into mathematical proofs. At a conference, Brouwer once explained that we should not accept the principle of the excluded middle because we do not always know which one of the two disjuncts is true. Someone in the audience yelled, "Well, maybe we don't know which one is true, but God surely does." To which Brouwer replied, "Well, you must know God very well." One can have either of the following 2 reasons for not admitting metaphysical notions into mathematics. Either because one thinks that mathematics is more evident than metaphysics, and that therefore mathematical knowledge should not depend on metaphysical knowledge, or because one accepts that mathematics depends on metaphysics, but one holds that as a metaphysical view, Platonism, for example, is false. Now, Brouwer himself was an example of this second attitude, his pupil Heiting of the first. But in both cases, what one is left with is the same. The task that remains is to develop mathematics as an edifice of mental constructions. To experience a mathematical truth is to experience that a certain construction in the mind has succeeded. This experience may be either direct, in the case the subject has actually carried out the construction, or indirect, in case the subject sees that a certain construction method will, if followed through, give the direct experience sought after. But there is nothing to mathematical truth outside mathematical experience. So here's a quote from Brouwer. "Truth is only in reality, that is, in the present and past experiences of consciousness. But expected experiences and experiences attributed to others are true only as anticipations and hypotheses. In their contents there is no truth. There are no non-experienced truths." Now here's a second example of the intuitionistic way of looking at mathematics. Unlike the first, which was the example of 2 plus 3, this will be a negative example showing something that intuitionistically does not work. Right, so of course this is a perfectly hackneyed example, but it's still forceful, so why not show it again? Consider the problem whether there are irrational numbers a and b, such that a to the power b is a rational number. In classical mathematics one may reason as follows. Either the square root of 2 to the square root of 2 is rational, or it is not. If it is rational, then we can answer the question in the affirmative by setting a equals b equals square root of 2. If it is not rational, let a be the square root of 2 to the power square root of 2, and let b be the square root of 2. Then a to the b is the square root of 2 to the square root of 2, and that thing to the square root of 2, which equals 2, which is rational. So either way, we have a solution. But which of the 2 obtains? The reasoning does not show what the value of a should be. It does not give us a construction for a. Intuitionistically, this argument is therefore not acceptable. For an intuitionist to say that 2 numbers a and b as required exist is to say that we have a mental construction for them. for there is no mathematics on that view outside of what we construct in the mind. Now, as it happens, there is an intuitionistic construction for such A and B using an intuitionistically acceptable theorem established by Gelfand that implies that the square root of 2 to the square root of 2 is irrational. The constructions that Brouwer has in mind are based on the intuition of time. Right, it's the intuition of time that you construct out of. This notion he had adopted from Kant. In Brouwer as in Kant, intuition is a technical term. Mathematics deals with purely formal objects. Like Kant, Brouwer held that time is required for thinking of any object whatsoever. It then becomes plausible to base mathematics on time, as the notion of a formal object is quite close to the notion any object whatsoever. Unlike Kant, Brouwer made a sharp distinction between subjective time, inner time consciousness, and objective or scientific time, time as it figures in physics and that you can see on a clock. Mathematics, according to Brouwer, is based on subjective time. Kant's pure intuition of space Brouwer did not borrow, for he held that the discovery of non-Euclidean geometry had shown that the notion of such an intuition is meaningless. Nevertheless, we do have a direct intuition of a continuum, but this is the continuum formed by the flow of time. Our prime intuition of a continuum, according to Brouwer, is not spatial but temporal. The intuition of time is part of pre-linguistic consciousness. Mathematics, therefore, according to Brouwer again, is essentially languageless. It studies non-linguistic constructions out of something that is given but not of a linguistic nature. And the development of intuitionistic mathematics consists in making constructions starting from this given, that is, from out of the intuition of time. For example, Brouwer wrote in his dissertation, "The only possible foundation of mathematics must be sought in this construction, under the obligation carefully to watch which constructions intuition allows and which not." And indeed, what intuition allows need not be immediately obvious. It takes an exploration. Simply knowing the ultimate ground of mathematical truth, knowing the basic intuition, does not mean that one thereby at once knows all that can be obtained from it. One has to see what principles are valid and which are not. This takes thought and in some sense careful experimenting. In this respect, Intuitionism is no different from Platonism. It is therefore easy to see that Brouwer would have agreed with Gödel when Gödel said, "To apply a position beyond its limit of validity is the most vicious way of discrediting it." This is also true of the emphasis on intuition. Appealing to intuition calls for more caution and more experience than the use of proofs, not less. So now follows a brief digression. From the characterization given so far, one can see the main differences between Intuitionism and Formalism, and between Intuitionism and Platonism. Unlike Formalism, Intuitionism does not hold that mathematics is primarily a matter of language. Unlike Platonism, Intuitionism does not hold that mathematics is concerned with the realm of objects that exist independently of us. Instead, it is about constructions in the mind. In this sense, Intuitionistic mathematics is free. It is not constrained by anything outside. The subject creates the mathematical universe and is alone responsible for it. In many ways, the Intuitionistic and Platonistic views on mathematics are opposites. However, each in their own way, they both stress that mathematics is not at root of a linguistic nature. For both the Intuitionist and the Platonist, language can only have a descriptive function and not a creative one. As Brouwer put it, formal language accompanies mathematics just as the weather map accompanies the atmospheric processes. Right, but the weather map does not bring about the weather. Right, it just describes it. End of digression. As mentioned, it is also the intuition of time that provides us with an intuition of a continuum. In classical mathematics, there are alternative but often equivalent ways to analyze continua. What they have in common is that the continuum is analyzed as an infinite set of discrete elements. This set is of a cardinality that is certainly beyond constructive means. But for an intuitionist, the cardinality is not even the main defect of the classical analysis. Because the intuitionist will say that there's a defect, right, in the classical analysis. The main defect is its atomistic conception of the continuum. The atoms are the real numbers. They have an actually infinite decimal expansion, and it's always determined what the nth decimal in the expansion is, whether we know it or not. And this is responsible for their discreteness. The real numbers are lying apart from one another. But Aristotle already pointed out that treating a line or a continuum as a collection of discrete points cannot do justice to its continuous nature. And Hermann Weyl put it in a particularly felicitous manner when he said, "One should not forget that in the continuum of classical real numbers, the individual elements are exactly as isolated from one another as, for example, the whole numbers are." In a true continuum, every part is itself again a continuum. A continuum is homogeneous in the sense that, if one keeps dividing it into parts, one never arrives at something that is not continuous, not even ideally or in the limit. Of course, one finds in classical analysis defined notions of continuity, but these are not basic. A set of points which is continuous according to such a definition is still a set of discrete points. But such defined notions are motivated by and dependent on the prior grasp of intuitive continuity. Such a grasp is necessary to motivate such definitions and to verify the extent to which they faithfully reflect the properties of continuity. Brouwer insisted that discreteness and continuity are mutually dependent notions and that the one cannot be reduced to the other. So here's a quote from Brouwer's dissertation again. "Continuity and discreteness occur as inseparable complements, both having equal rights and being equally clear. It is impossible to avoid one of them as a primitive entity, trying to construe it from the other one, the latter being put forward as self-sufficient." Right, so according to Brouwer, either you have both notions of discreteness and continuity, or you have none of them. Right? But what you cannot do is start from the one and then, through some clever definitions, arrive at the other. When around 1689 Leibniz wondered how to capture this intuitive continuity mathematically, he wrote, "There are two labyrinths of the human mind, one concerning the composition of the continuum and the other concerning the nature of freedom, and they arise from the same source, namely infinity." Now, as far as we know, Brouwer never made an extensive study of Leibniz, but the solution to the question of the mathematical modeling of continuity that Brouwer came up with depended precisely on the other notion that Leibniz mentions, freedom. So let's see how. Imagine that you have a collection of mathematical objects at your disposal, let's say the natural numbers. Pick out one of them and note the result. Put it back into your collection and choose again. You may choose a different one or the same. Note the result again and put it back. For example, perhaps you chose 12 and then 3. Making further choices, you may arrive at 12, 3, 81, 12, 221, and you can continue from there. A choice sequence is what you get if you think of the sequence you're making as potentially infinite. So in French, suite de choix, German Wahlfolge, and in the original Dutch, Keuzerij. These are all literal translations of each other. The two sequences given above, so the sequence 12, 3 and 12, 3, 81 and so on, are initial segments of the choice sequence. Initial segments are always finite, right, by definition. Now, we cannot make an actually infinite number of choices, but we can always extend an initial segment by making a further choice, or at least ideally we can do this. This potential infinity of the choice sequence we indicate by 3 dots. Let's call this choice sequence alpha. So here we have alpha. We'll see some more of alpha later on. Although choice sequences are never complete, the subject can generate them in parallel, in zigzag fashion. Make a few choices for alpha, then for beta, then for gamma, then turn back to alpha to extend it a bit further, and so on. And that's often useful. Now, Brouwer used choice sequences to give a mathematical analysis of continua, such as those of space and time. We will look at the example of the spatial continuum of the straight line. To this purpose, we use choice sequences of rational intervals instead of natural numbers. A rational interval specifies a part of the continuum by saying what the lower and upper boundaries of that part are, where these boundaries have to be rational numbers. It can be shown that it means no loss of generality if one demands that at choice V we choose a rational interval of the particular form indicated on the slide. Right, so V just indicates which of your choices this is, your first, second, third, and so on. And A is the number that you freely choose. And then you limit yourself to choices of this form. Brouwer then defines a point or real number as follows. And this is a quote. We consider an indefinitely proceedable sequence of nested lambda intervals, lambda v1, lambda v2, lambda v3, and so on, which have the property that every lambda vi plus 1 lies strictly inside its predecessor lambda vi. That it's properly contained in its predecessor. Then, according to this definition of lambda intervals, the length of the interval lambda vi plus 1 at most equals half the length of lambda vi, and therefore the length of the intervals converges to 0. We call such an indefinitely proceedable sequence of nested lambda intervals a point P, or a real number P. We must stress that for us the point P is the sequence lambda v1, lambda v2, lambda v3, and so on itself, not something like the limiting point to which, according to the classical conception, the lambda intervals converge, and which could, according to this conception, be defined as the unique accumulation point of midpoints of these intervals. Every one of the lambda intervals, v1, v2, and so on, is therefore part of the point P. So it's worth stressing that according to Brouwer, the choice sequence growing in time is itself the real number, right? So according to Brouwer, real numbers are growing objects.
And not a class of sequences, no? Just every
well, so in principle, every individual choice sequence satisfying this convergence condition will determine a real number. But in practice, of course, you will rather speak of what classically you would call an equivalence class and what Brouwer calls point cores. Because it may be that you have different sequences, but that you can show, right, that they always, just as in the classical case. But nothing depends on that, really. So it's the growing sequence which is itself the real number. It would be incorrect, therefore, to say, as for example Hintika does, quote, one can, according to Brouwer, construct an infinite choice sequence of zeros and ones, but we do not thereby come to know what the real number is whose binary expansion one thereby obtains. For in Brouwer's construal, one knows very well what that real number is, for it is the proceeding sequence itself. It is not the case that the choice sequence is a method to approximate a real number that lies in transcendent reality, waiting to be reached by the subject. Now imagine that besides the choice sequence alpha, which we started a few minutes ago, you also started in parallel a choice sequence beta, which starts 12, 3, 81, 12, 221, and you haven't made further choices yet. So in this case, the initial segments of alpha and beta obtained so far are identical. Does this mean that the choice sequences alpha and beta are also identical? We cannot say, as there is no fact of the matter. Nothing can be said about whether the two sequences will develop in the same way in the future. The choices made so far are the same, but they don't have to be in the future. The future of each sequence is still open, it's not fixed, and it only depends on our own free choices and is not already determined. More generally, a choice sequence cannot at any stage have or lack a certain property if that could not be demonstrated from the information available at that stage. In fact, one way, of course, you have ways to ensure that alpha and beta will come to diverge, right? Again, this is also up to you. You can, because you're free to pose restrictions on your own choices. So you may want to say, well, from now on in alpha I will choose only odd numbers, and in beta I will choose only even numbers, right? Once you have imposed that restriction, which stipulates that alpha and beta are to have certain properties, right? Then you can just say right away, alpha and beta are not the same choice sequence because you know different things about them. And how do you know these things? Well, because you stipulated them yourself. And you're free to do this. And it's not just that you're free to do this, but you even have to. For example, if you want to say intuitionistically, there is a real number 0, right? That just means to say there is a choice sequence in which every choice you make is 0, right? The same for any definable rational number, right? Otherwise, you wouldn't have those numbers, because the only real numbers that exist are the ones that you construct. So if you don't take care of constructing 0, there will be no 0. So it was in particular choice sequences that Brouwer was thinking of when he wrote, in intuitionist mathematics, a mathematical entity is not necessarily predeterminate, and may, in its state of free growth, at some time acquire a property which it did not possess before. Intuitionistically, we can only assert something if we have experienced its truth by obtaining evidence for it. So it is not true that either alpha and beta are identical or they are not. We have no right to assume now alpha equals beta or alpha does not equal beta. So even minimal experience with choice sequences makes it clear that whatever universally valid logic may look like, it will not be classical logic. For points, in the sense of Brouwer's definition given above, this undecidability models the fact that a point on the continuum is not a dimensionless atom, but it's rather a halo, right? It's like a blob that you cannot really reduce or think of as a dimensionless entity. This way, the intuitive continuity of the line is preserved. That choice sequences are incomplete or unfinished objects may guarantee properties that are philosophically desirable when modeling the continuum, but may at the same time seem to make them unworkable in practice. For if mathematics is to be based on constructions, what place is there for objects that at no stage have been completely constructed? Fortunately, there is a continuity principle. Essentially, this principle says that all one has to know to make a predication of some choice sequence is an initial segment, hence a finite amount of information. And unlike the sequence itself, its initial segments are always given in finite constructions. So here's a formulation of a particular continuity principle. This is called weak continuity for numbers. So in this principle, WCN, alpha and beta range over choice sequences of natural numbers, m and x over natural numbers, and alpha over bar m means the initial segment of alpha of length m. So that's just a finite sequence. Right, and basically what it says, if for every choice sequence alpha there exists some natural number such that the relation A holds between that sequence and that number, then you can indicate a certain initial segment of alpha such that any other sequence beta which will share that initial segment will also have that property A. So here you see this is sharing initial segments. And it's called weak continuity for numbers because the principle only says something about each alpha individually, so it's a local continuity. Right. From weak continuity, a particular theorem and a corollary follow that show that intuitionistic analysis is not just an amputation of classical mathematics, but contains new results that are classically not acceptable. So here's an example. The Dutch intuitionist Wim Veldman showed the following. From weak continuity, one derives the Continuity Theorem. A real function whose domain of definition is the closed segment, the unit continuum from 0 to 1, is continuous on that interval. So it says that any real function f, which is total on the unit interval, is continuous on the unit interval. And from this, one obtains immediately the unsplittability of the continuum, which is this. So unsplittability of the continuum says the continuum cannot be split into two non-trivial subsets. If you have that R is a union of some A and B which are disjoint, then either A or B must be equal to R itself, to the continuum itself. And the argument in the presence of the continuity theorem, of course, is the following. Suppose that you have found such an A and a B which are disjoint but together make up the whole continuum. Then you could define some function f on it which assigns 0 if the argument is in A and 1 if it's in B. But then by the continuity theorem, well, f is total, right? So by the continuity theorem, f should be continuous. But that's clearly impossible in this case. Hermann Weyl announced the continuity theorem in 1921, but this is not really the same strong result as Brouwer's. Weyl defined real functions in such a way that they are continuous by definition, namely by mappings of the intervals of the choice sequence determining the argument to intervals of the image sequence. In this way, the function type is reduced. Right, a function from, instead of a function from the reals to the reals, you turn it into a function of initial segments to initial segments, which is really, because initial segments are finite sequences, is really a function of the natural numbers to the natural numbers. Brouwer, on the other hand, established the continuity of functions from choice sequences to choice sequences. Now, I already mentioned that you have the immediate consequence of the unsplittability. And classically, of the splitting the continuum, of course, is a trivial matter. For example, you can assign 0 to x if it's rational and 1 if it's irrational. And the reason for this difference is ultimately that classically R is a set consisting of elements isolated from one another and hence separable from one another. Whereas intuitionistically, R is an unfinished whole of choice sequences on which equality is not generally decidable, as we saw. And by the refrain of the intuitionist song, if we have no method to decide equality of choice sequences, then in general there is no fact of the matter whether two sequences are equal or not. And similarly, what is behind this really is that you can construct choice sequences, for example, depending on still open problems, of which you can, on the one hand, prove that they converge, but on the other hand, you do not know yet. All right, this is dependent on coming to know the solution to some open problem. You do not know yet whether they will converge to a rational or an irrational, for example. Something else shown by this, or, well, it's not really something else, but something worth making explicit, is that this also constitutes a strong counterexample to one form of the principle of excluded middle, namely the universally quantified form. For all x, either you take some property p, and then for all x, either x will have that property or it will not have that property. But here, because of unsplittability, for example, we have, it's not just that we have no evidence to say that any real number is either rational or irrational, it's that you can show it's actually false to assume that that you can say this. So that's stronger, that's strong negation. Of course, this is the universally quantified version of the principle of excluded middle. Of course, the simple principle P or not P, although not considered generally valid intuitionistically, it's certainly not false. Right, because in the sense of strong negation, because then you would get not P or not P, which also intuitionistically is equivalent to not P and not P, right? So that wouldn't. So intuitionistically, you cannot have strong counterexamples to excluded middle, but in the quantified form, you can. So this was, I think, the first strong counterexample that Brouwer obtained. He obtained this in 1927. And then he developed a method systematically to generate strong counterexamples. And this is the theory. This is now known as the theory of the creating subject. And I can say something about this too. So you introduce a modal operator box N A, which stands for the creating subject experiences the truth of proposition A at time N. Then Kripke and Kreisel made explicit some principles. Let's look at the following three. The first says that basically says that evidence never gets lost. So if you obtain full evidence for A at some time N, then at any later moment you will still have full evidence for A. That's the first. Then the second says that at every moment the creating subject can decide whether it has full evidence for A or not. So the idea of having full evidence is decidable. You know whether you have sufficient evidence for A or not. And the third says A holds exactly if the creating subject has full evidence for it at some moment. Kreisel dubbed this the principle of Christian charity, right? Because there may seem some charity in the notion that if something is true, you will find out at some point. An alternative name he suggested is the principle of infinite vanity. Well, that you can also see, right? There's something vain about thinking that if something is true, you will find out at some point. But these somewhat dramatic names, of course, only have their dramatic ring if you look at things from a classical point of view. Because intuitionistically, it's not surprising at all that you have this principle number 3. Because for an intuitionist, a proposition's being true precisely means that at some point you found the proof. Right? You already have it. To say A is true is to say I have a proof of it. So, and if you have a proof, you must have obtained this at some moment. And the other direction is trivial, right? That's a kind of soundness. You say, if I have at some moment the proof of something, then that means that this something is true. So one way of looking at these 3 principles is that together they more or less define the intuitionistic conception of truth. On the basis of these 3, On the basis of these 3, one can associate to each proposition A choice sequence alpha that, so to speak, witnesses A. You can think of alpha as a bookkeeping device for keeping track how things are in your effort to prove or disprove proposition A. So just at the moment n, right? If by the moment n you have a proof of A, you choose 1, and you will keep choosing 1 in the future. But until that is the case, you just keep choosing zeros. And of course, it may well be that A is actually false, and then you will just be choosing zeros forever. Otherwise, the sequence alpha will be 1 from the moment that you have a proof of A. Now, related to this, something called Kripke schema KS, which just says to any proposition A you can associate a choice sequence alpha which will be 1 at some point if and only if A is true. Right, and the justification is that, well, because mathematics consists in your own activity, you can keep a log of your own activity, so you can, at any moment, you can tell whether you have or have not obtained by then a proof of A, so you can then construct the sequence alpha accordingly. That's the whole idea. Now, in fact, Kripke schema was formulated by Brouwer before Kripke in his paper from 1954, Points and Spaces. But in his actual constructions of counterexamples, he never refers to this, and it's rather left implicit. For example, some years before, he showed the following 2. He showed that it's actually false to assume that for any real number, if it's not larger than 0, then it's larger than 0. And he also showed that it's actually false to assume that if some real number x is not equal to 0, then it is apart from 0. So apartness is stronger than inequality because it means that you also have some positive information on how far apart these two numbers are, a and b. So apartness is stronger than mere inequality. It's stronger because here you have no positive information and here you do. Now, in the proofs of these counterexamples, choice sequences are employed that depend on the creating subject having experienced either the truth or the absurdity, which is the intuitionistic term for falsehood, of a particular mathematical assertion. These sequences are therefore not law-like, right? These sequences are not, they essentially depend on free choices and on your free mathematical activity, and you cannot specify them beforehand by some algorithm. And these methods are very powerful. For example, you can not only prove that the continuum as a whole cannot be split, but you can even prove that the subset of the continuum of the irrationals cannot be split. So that only goes to show, of course, how intricately connected the continuum is on the intuitionistic point of view. Even if you just take out the irrationals, you cannot lift them out of the continuum, and if you do consider them, then you cannot think of them as made up of two disjoint subsets. Now Brouwer, as I mentioned, perhaps, he did not explicitly state the continuity theorem. Instead, he proved a stronger theorem, namely uniform continuity. And then, of course, well, the simple continuity theorem, of course, is an immediate consequence of uniform continuity. And that's the way Brouwer presented things. But as I mentioned, Veltman later on showed that you can obtain simple continuity directly out of the weak continuity principle. Now, in his proof of uniform continuity, Brouwer relied on a theorem that goes beyond the weak continuity principle for choice sequences, as follows. An application of weak continuity to some predicate A determines a set of initial segments that suffice to calculate an x such that some relation A holds between a choice sequence alpha and the number x. And such a set is called a bar. Right, so we saw that by the continuity principle. Maybe it's worth putting that up again. The continuity principle says, right, if you have a means or a construction method that assigns to every choice sequence alpha some number x, then there is a natural number m such that any sequence which coincides with alpha on the initial segment of length m will stand in the same relationship to that natural number. So what you can do, for example, you can look at all choice sequences with that same initial segment of length m. And the idea that's so then you have a what Brouwer called a spread or a tree of finite initials of finite segments of initial segments, and Brouwer calls that it's what he calls a bar, because any path through the tree will at some point hit. You will have sufficiently extended the initial segments to coincide with that initial segment of alpha, which suffices to bring it about that this relation A holds. So if you think of all choice sequences as forming a tree, then if you have a set of nodes in that tree such that each path through the trees at some point intersects that set of nodes, then that set is called a bar. And to see if one can arrive at stronger results in analysis, one would have to know whether bars have certain structural properties. And Brouwer found such a property and proved in 1927 his so-called bar theorem, which may be formulated roughly as follows. If B is a bar, then the collection of nodes that have just reached B, the bar B, admits of a well-ordering. Right? Because you can imagine that you can define some set of nodes in the universal tree made up of all choice sequences, and that you might be able to prove, in fact, that any choice sequence will at some point intersect that bar, without thereby having a construction, a well-ordered construction for that bar. But Brouwer says that, in fact, whenever you have a bar, there will be a well-ordered construction for it, or more precisely for you have a construction for a smaller tree, or potentially smaller tree, which also will be a bar. And this is a very powerful insight, for it allows one to use induction in reasoning about bars. And you can see some of the power of that insight, of course, if you just compare the quantifiers in simple continuity with the order of quantifiers in uniform continuity. Right? Because in uniform continuity, the delta that you're going to find may depend only on epsilon, whereas in simple continuity, right, the first quantifier for the x will be in between the epsilon and the delta, so delta may depend not just on epsilon but also on x1. That's precisely, of course, why it's called uniform continuity. And for this, but of course, if you want to say something which should hold for all x1, right, then it becomes very plausible that you should need some global information, certainly more global information which goes beyond the local information that the simple continuity principle for choice sequences will give you. So this also explains why, for example, Veltman was able to prove simple continuity from just the continuity principle for individual choice sequences, but you need something stronger to prove uniform continuity. And that something stronger is actually what Brouwer found first, or at least that's what he presents as coming first, and which is this Disbar theorem. Now, generally, the number of immediate successors of a node in a tree, for example, in a tree of choice sequences, may be finite or infinite. A tree in which every node has only finitely many immediate successors is called a finitary tree or a fan. One also says that such a tree is finitely branching. A corollary of the bar theorem is the so-called fan theorem. If B is a bar for a fan, we can effectively determine a bound on the length of the paths to the bar. It is of some interest that the fan theorem, of course, is the contraposition of Koenig's lemma. But the fan theorem was proved before Koenig's lemma. And that is rare, relatively rare. Usually what happens in constructive mathematics is that you prove theorems of which some classical version or something like it in classical mathematics already exists. But in the case of the fan theorem, what happened was the opposite. Well, that's not quite precise. I mean, it is true that the fan theorem was proved before Koenig's lemma, but it was not the case that Koenig's lemma was proved because Denis Koenig, who proved the Koenig's lemma, saw the fan theorem and then looked for a classical proof. I mean, that's not the history at all, but it just happens to happen that way. Now, so it turns out, which is most useful, that you can also represent the unit continuum as a fan. Namely, of course, there are a million ways of doing this, but one of them is if you restrict yourself to making choices of intervals of this particular form, with the condition that a plus 2 should equal or be larger than 2, and should equal or be smaller than 2 to the n plus 1, then you know that for each n, only finitely many choices will be possible. So when you make your nth choice, because of the fact that you have to choose something of that form specifying, satisfying that condition, you know that there will be only finitely many choices possible. So you get a finitely branching tree. But you can also show that you actually cover the whole unit continuum this way. And it is this way that Brouwer could prove theorems about the continuum, such as the uniform continuity theorem, because that's what he used it for, from a theorem on the constructively more tractable finite hairy trees. And this shows the power of the Van theorem. Given some suitable bar, the Van theorem enables one to prove theorems about the continuum by proving theorems about choice sequences of a certain bounded length. And the latter certainly are much more manageable than the continuum itself. Now, Brouwer seems to have proved the bar theorem solely for the purpose of establishing this corollary, namely the Van theorem. From a classical point of view, as I mentioned, the Van theorem is the contraposition of Koenig's lemma, which was proved later, namely if a Van contains infinitely many nodes, it contains an infinite path. But intuitionistically, Koenig's lemma is not valid, so it cannot be used to obtain the Van theorem. The problem with Koenig's lemma, for an intuitionist, is that it doesn't enable one actually to construct an infinite path through the Van, hence the need for an intuitionistic proof of the bar theorem. An intuitionistic proof of the bar theorem, because then the Van theorem will be a special case. Brouwer's proof of the bar theorem strongly depends on the intuitionistic notion that truth of a proposition consists in having a construction for it, on his conception of proofs as mental objects, and on reflection on the kinds of mental acts used in constructing proofs concerning bars. In effect, Brouwer engaged in a type of phenomenological analysis of these acts to arrive at his theorem. Phenomenological analysis would be necessary even on a more general level than that of the bar theorem, namely on the level of choice sequences as such. An analysis of the notion of mathematical construction is needed to show that choice sequences are a genuine type of object, and moreover are generally mathematical objects. Right, for example, Wittgenstein and Gödel at some point, well, Wittgenstein always, but Gödel at some point said, well, yeah, choice sequences may be objects, right, but they are not mathematical objects. They are empirical objects of some sort. Gödel later came to change his mind, as is documented in the correspondence with Bernays. At some point, Gödel says in the letter to Bernays, well, the last 2 weeks I've been thinking hardly about choice sequences again, and now I think that they are objects of finitary mathematics. Which is an interesting remark in itself, because usually you would like to think of finitary mathematics as a proper subset of classical mathematics. But if you think, well, choice sequences are objects of finitary mathematics, I mean, they are certainly not objects of classical mathematics, so then you would also have to draw the conclusion that maybe finitary mathematics is not a proper subset of classical mathematics. And there are in fact construals of finitary mathematics on which that is not at all implausible to say, but that's something for another time maybe. So yes, you would need some analysis to show that choice sequences are objects and that they're also mathematical objects. And such an analysis would show that by considering mathematical objects to be mental constructions, one can obtain objects that are not acceptable to classical mathematicians, precisely because they insist that mathematical objects do not depend on the mind and its properties, and in particular, that mathematical objects do not depend on free choices. This analysis remained to a large extent implicit in Brouwer's writings, but within the framework of, for example, Husserl's phenomenology, it is possible to complete his indications to a full analysis. Yet the question may be raised whether a philosophical analysis of choice sequences is really necessary in view of the so-called elimination theorems. According to these elimination theorems, propositions referring to choice sequences are equivalent to propositions that do not refer to choice sequences. In fact, such theorems exist only for very specific classes of choice sequences, not for choice sequences in general, and moreover, it can be argued that even for the specific classes in question, so classes of choice sequences for which we do have such theorems, these theorems are not sufficient to eliminate choice sequences or to explain them away. And there are 3 reasons. For simplicity, I will discuss these for the case of lawless sequences, that is, sequences where each and every of your choices is completely free and you have imposed no restrictions on your choices. In fact, you may think of this as a second-order restriction, namely the restriction that there will be no first-order restrictions. So So let's think of lawless sequence as one for which there are no first order restrictions whatsoever. Now, Troelstra, developing earlier work by Kreisel, has presented a formal system LS describing lawless sequences together with a mapping TOL into a subsystem without variables for lawless sequences, IDB, such that the following three hold. So if the first says that if you're already in the subsystem, then the translation TOL will yield equivalent statement. The second says that within the system for lawless sequences, you can prove that any proposition A will be equivalent to its translation under TOL. And the third says that if you can prove some proposition in LS, then this is equivalent to saying that in IDB, so in the subsystem, you can prove its translation. So together these three give a very strong sense in which you can say that, well, in which some people have said that this shows that lawless sequences, for example, can be eliminated. Right? So you don't really have to accept them into your ontology. You can just write out your propositions that refer to them, and then you apply the translation and you obtain equivalent statements that do not refer to them.
What does IDB one mean?
Oh, so IDB stands for inductive definitions, and the B.
Bounded.
Yeah, it escapes me for the moment, actually. Well, I just can't remember for the moment. But it's bounded seems quite plausible, actually. Now, I think there are at least three reasons why a translation such as this TOL has no ontological consequences whatsoever. Very generally speaking, you could say, well, this is because it's a translation and not an interpretation, in the sense that Jørgen Sundholm has given to these two terms in 1983. But we can see how it works out in detail. So the first is that the translation yields equivalences, right? You get statements of the form A is equivalent to TOL of A, where A quantifies over lawless sequences and TOL of A does not. But as A is a component of this statement as a whole, the lawless sequences are still involved. And being part of a genuine statement, A can therefore not be regarded as somehow deficient or quantifying over objects that do not really exist, whereas everything in TOL of A does, in some sense, really exist, right? You have within one and the same statement, you're referring all the same. You're still referring to these lawless sequences. For this reason, Kreisel himself actually suggested that such translations should not be understood as elimination theorems, but rather as giving a complete analysis of lawless sequences. For some unfortunate reason, these theorems are still generally known as elimination theorems. But Kreisel himself had already suggested that they are really not. Secondly, to speak of elimination might falsely suggest that the intuitive continuum can be regarded as a discrete point set after all. Even if statements quantifying over lawless sequences are equivalent to statements that do not, the fact remains that we should think of the continuum as analyzable into, among others, such sequences and not into elements of a set. And in a slightly different way, this point was also made by Dermot when he wrote, "No one would seek to construct a theory of real numbers in terms of choice sequences if these appeared only in the thorough disguise provided by this translation into the subsystem IDB." Right? Because the translation, actually the results that you get out of translating these statements are not particularly intuitive to begin with. So as Dermot said, if all you had was really that subsystem, then you would never think of analyzing the continuum in terms of choice sequences, but for good reasons that is what you should do. And the third reason is that these translations occur in the context of axiomatizations of choice sequences. In this case, the particular class of lawless sequences. These systems should not be confused with the sequences themselves. Axiomatizations are a way to present mathematical content, but they are not identical to this content. Lawless sequences have been axiomatized, in fact, in different and not always equivalent ways by, for example, Kreisel, Myhill and Troelstra. Nevertheless, something remains the same, namely, these axiomatizations are all about lawless sequences. Clearly, it is not the case that we were first in the dark about this and then learned it from finding certain mappings between the formalisms. These sequences, or any other mathematical object, can simply not be identified with any particular axiomatization, let alone with any particular full formalization. And moreover, doing so would force one to accept the implausible view that Brouwer's theorizing before the introduction of axiomatic theories was in fact about nothing. Now there's also a positive aspect to such translation theorems. Of course there are many. But one of them is that they show the coherence of the notion of choice sequence involved, at least relative to the theory translated into. Now it is true that there is no contradiction between the classical and intuitionistic systems of analysis as such, as key terms such as real number and function are construed differently in both theories. The classical and intuitionistic ontologies are simply different. In this sense, for example, the Continuity Theorem and the Uniform Continuity Theorem do not contradict classical analysis, nor vice versa. Yet there is a different and deeper type of contradiction brought about by this situation. When one realizes that both the classical and the intuitionistic analysis try to capture the same pre-theoretical continuum. This is one of the senses in which intuitionism is not merely an alternative to classical mathematics, but actually claims philosophical priority. In other words, intuitionism urges a revision of classical analysis. And of course here too the situation is perfectly symmetric, right? And a classical mathematician may say, no, precisely the fact that intuitionistic analysis also tries to model this intuitive continuum but comes out with something different from what we are doing shows that there must be something very wrong with the intuitionistic analysis, right? So it's entirely symmetric, the situation. Now in general, there are three different ways to see the relation between philosophy and the actual practice of mathematics. First, one may view this as follows. Philosophy describes but has no right to impose limits or other changes on mathematical practice. This may be called non-revisionism. The second point of view, which may be called weak revisionism, holds that philosophy tests, according to some philosophical standard, what is acceptable in mathematical practice, right? But it does not extend or suggest extensions to mathematical practice. It just takes mathematical practice and says, well, this you can do and this you cannot. But it does not say, oh, here's something else you could also do. You haven't, but you could. So that may be called weak revisionism. And the third possibility is to say that philosophy has the right to impose, according to some philosophical standard, limits, but also extensions of mathematical practice. And this may be called strong revisionism. And in this terminology, intuitionism is of course a form of strong revisionism, because it doesn't only say the ontology of classical mathematics is much too big. It should be cut down to what can be constructed according to some notion of what is constructible. But it also suggests extensions to the classical ontology. It also says, well, there are also objects that are not known in classical mathematics, but that should be introduced all the same, namely choice sequences. Now today the most influential position of these three certainly is non-revisionism, under the name of naturalism. And this is not so much a philosophical as a social fact. Naturalism is meant here not in the sense of naturalized epistemology, but as the position that no point of view external to the practice of mathematics, in particular no philosophical one, can demand changes in mathematical practice. And of course almost all of today's mathematical practice is classical. Now naturalists may well acknowledge that it's possible to exaggerate the agreement between practicing mathematicians. For example, within the field of contemporary set theory, there is much disagreement actually over the acceptability of various principles and of certain very large cardinals. Also, obviously, there's the small but significant minority of constructive mathematicians, among whom the intuitionists, that persist in rejecting various principles from classical mathematics. But a naturalist might go on to say that the disagreement is considered not to be amenable or not in need of philosophical adjudication. Rather, mathematics with its methodologies that have been developed through the ages could take care of itself. A problem with that line is that those disagreements are motivated and kept alive by philosophical considerations of the mathematicians themselves. Intuitionism keeps insisting on the traditional foundationalist concerns in the philosophy of mathematics. What is the nature of mathematical objects and how can we have knowledge of them? I will skip a tiny part for reasons of time and come to conclusion, or more precisely a concluding remark. It has been suggested that philosophical investigations cannot contribute to the foundations of mathematics for the reason that the only type of rigor possible is formal rigor. As Gödel remarked, this suggestion is certainly question-begging. When formalizing a certain subject and its intuitive notions, surely some other kind of rigor must have been at work in devising the axioms and in verifying that they hold for the intended meaning. Kreisel has called this other kind informal rigor, and has emphasized that it's often sufficient to settle mathematical questions. Informal rigor is not to be thought of as a new kind of rigor or as a new method coming in from outside mathematics that competes with the mathematicians' traditional methods. It's rather simply the kind of rigor that mathematicians have always been applying when not working entirely formally. And unlike rigor, formal systems are a late arrival in the history of mathematics. This includes, of course, the correction of earlier mistakes by the application of yet more informal rigor. And of course, both kinds of rigor, formal and informal, may be combined by first analyzing a mathematical problem informally but rigorously and then formalizing the solution. Conversely, formal problems may often be due to insufficient prior informal analysis. Moreover, intuition takes precedence over formalization in the following sense. As a formal system is itself essentially of a mathematical nature, the relation between such a system and a model for it is a relation entirely internal to mathematics, even if you think of mathematics in a purely extensional sense. Therefore, the method of formalization of theories and then determining the method of formalizing theories and then determining their mathematical models presupposes that one already has determined what the nature of mathematics is and what objects it comprises. It follows that specification of formal theories and their models ultimately cannot serve to determine the meaning of mathematical propositions. So a shift of emphasis from intuition and meaning to formal theories and their models is actually a shift of grounds. For this reason, Gödel spoke of the hopelessness, in German Aussichtslosigkeit, of doing anything decisive in foundations by means of mathematical logic. Now that was an insight that Brouwer shared, but to a further extent than Gödel, he was prepared to accept and exploit the consequences of it. Thank you.
Je crois que c'est un des aspects les plus forts, les plus intéressants d'une approche constructiviste, c'est qu'on obtient la continuité directement de l'encadrement théorique, c'est-à-dire, pour le dire d'une façon grossière, toutes les fonctions sont continues. Le problème, évidemment, est
toutes les fonctions
constructives.
Non, il y a des fonctions constructives qui ne sont pas continues.
Oui, voilà ce que je veux dire. Tout dépend évidemment du choix de la métrique. Hein. C'est ça qui force un peu la situation. Et qui donne des topologies différentes en plus. C'est que je pense qu'il y a les passages les plus importants, c'est que grâce à cette approche, on peut construire des topos où il y a une topologie absolument naturelle et il n'y a que des fonctions continues d'un côté. Et de l'autre, en théorie de la calculabilité, si on choisit de bons espaces topologiques, encore une fois, les théorèmes comme May-Jefferson, Rice-Shapiro donnent, pour les fonctions calculables, encore une fois, la continuité. Mais ce qu'il y a derrière, c'est le choix de la métrique, qui n'est pas toujours celle naturelle. Dans le cas des réels, par exemple, il faut passer par l'espace des Cantor, avec la métrique de l'espace des Cantor. Ce n'est pas la même chose que la topologie naturelle l'euclidienne sur les réels. C'est-à-dire qu'il y a ces prix à payer dont je ne connais pas tellement les sens profonds qui auraient d'impact sur d'autres disciplines, mais qui ont eu une importance très grande pour les applications à la calculabilité, à l'informatique, les domaines de Scott, sont tous dérivés de là. Mais qui évidemment, c'est un choix très fort, ça change des cadres d'une façon qui n'est pas gratuite. Il y a quelque chose derrière qu'il faut expliciter à chaque fois. Je sais pas si...
Oh, well, what you're saying, of course, that is all certainly the case, but it's very different from Brouwer's approach, which I've been describing. Because Brouwer does not choose a non-standard metric, right? You just take the ordinal metric. And it's also not the case for Brouwer that all functions on the continuum or on the unit continuum, right, are continuous. He says all the functions that are totally defined, right, or are fully defined, they will be continuous. But of course, he was also concerned with the question, well, then what about discontinuous functions, right? How do you think of those? Now, in a first approach, you could think of them as there are two approaches you can take, or at least two. The first approach that you could take is to say, discontinuous functions we get just by taking functions that are not fully defined, right? You just take subsets of the whole continuum, but not the whole continuum. And the second approach is really a more refined version of the first approach, where you just say, well, let us take, instead of the whole continuum, let us take subsets of the continuum which still satisfy a sufficient number of properties of the continuum that are of interest in the present context. And in particular, Brouwer looked into that approach, and it's for that reason actually that the paper in which he proves the Disbar Theorem and states and proves the uniform continuity theorem, the title of that paper is actually on the domain of definition of functions, because as soon as he has proved uniform continuity, he will then go on in the second part of the paper, well, what about non-continuous functions? Unfortunately, that part has been left out, for example, in the Van Heijenoord anthology, but at least it explains the title. But that's, of course, that's a different approach than choosing a very different, or maybe very non-natural metric, and then through that means arrive at functions that are always continuous, for example, which is not even the case for Brouwer.
The other metrics are not natural. They came out also for, the counter topology on counter space is natural in its own way, but radical changes in structural space.
But Brouwer was not venturing into that kind of direction.
I just have two points which looks like a kind of incoherence in that construction. I mean, incoherence is rather in the sense of the philosophical intention. Probably I'm wrong. And first thing, when you just introduce this free choice sequence in the general form, as you explained, just choice of natural number, it looks like you have natural number as already given and is already there. So you have something like actually infinite set of natural number, and then somehow it's, if you have the set, in normal classical, it looks kind of classical remain or background of the whole construction. And the second similar point, when you quantify over possible choice sequences, it's even stronger form, right? So somehow the idea is it's something developing, not finished. But then you quantify all of them. And that looks.
So, but in both cases, things are not what they seem. So in the first case, yes, you do. Well, in general, whenever you have a choice sequence, you'll ask, well, what objects am I going to choose? So indeed, you need some prior specification of some domain of objects, out of which you will then make your choices. And indeed, you can take the natural numbers for this, but Brouwer, of course, came up with an independent construction of the natural numbers, according to which you will not obtain the natural numbers as an actually infinite set, but as a potentially infinite one. He just says, well, I know, he has this. It all falls out of his analysis of the move of time, right? So maybe I should not elaborate on this right now, but to summarize, he says out of the move of time, you immediately, the first thing that you get is the notion of two different things that you have at the same time in your mind. And so that gives you two. Then by abstraction from that, you will get one. So genetically speaking, according to Brouwer, the number two is prior to the number one. And once you have that, then again, you know, time will move on. You get to some other stage. You make abstraction from this, and then you have the number two that you just had, plus this new thing, which will then be the number three. Time moves on. So this way, you will generate the natural numbers. But at no moment, literally, at no moment, you will have some actual totality of all the natural numbers. So he just says, no, but I do have a construction method, which I can just always. So that is how you get your natural numbers. And then when you quantify over them, well, of course, intuitionists have their own interpretation or their own reading of the quantifiers, right? So when you say, for example, for all choice sequences, there is a natural number, blah, 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 then how they interpret these quantifiers is to say, I have a construction method, which when you give me any choice sequence, right, I will then construct a natural number for it. So it's completely, it all remains completely intentional with an S, and never becomes extensional. This is also, but of course this problem or potential problem shows up elsewhere too, for example in the interpretation of implication, where intuitionists will interpret A implies B as, well, for all possible proofs of A, right, I have a method that will then transform such a proof into a proof of B. And then Gödel and others have objected early on, well, no, that's impredicative, right, because you're quantifying over all possible proofs, so that may well include possible proofs of A implies B. And but then again, for an intuitionist could reply, no, I mean, I just, all I mean is that I have a construction method that whenever you give me something that I recognize as a proof of A, will then give a proof of B. So it's rather, the intuitionist reading is rather certainly in the case of implication, it looks much more like a transcendental argument, right? What is known as a transcendental argument in philosophy. So you say, well, what are the conditions of possibility for any proof of A? And just on the basis of those conditions of possibility, you then come up with some construction that will give you a proof of B. But it all remains completely intentional. You never suppose that you have extensionally before you, so to speak, all the possible proofs or all the choice sequences. Or it's not, yeah. But of course, you're right. You can well expect. You should well expect that if you can make choice sequences to work, this means that there are all kinds of other things that you also have to interpret in non-classical ways. I mean, that is certainly true, yes.
Just a philosophical question. In this framework of Brouwer, how do you interpret the basic question of intersubjectivity? Of course, there is not one mathematician, but there are many mathematicians. And mathematics is a common is shared by many people.
Yeah. Yeah.
And it seems that if I take strictly what you said at the beginning, I mean, even writing about mathematics should be somewhat improper. I mean, that you have, everything should be done in the mind. But of course, we all know what all philosophical question and riddle that are communication between different minds. Yeah. And there is not. And of course, as soon as you imagine that there is more than one mind, I mean, well, I prefer intersubjectivity to objectivity. Mm-hmm. I think it's more accurate in this discussion. Yeah. How to take this into account?
Yeah. Well, so one way of thinking about this is that when Brouwer is speaking of the creating subject, so a subject who's creating all these mathematical objects and so on. So, well, you can think of this in two stages. So the first stage is that he's describing an idealized subject. Idealized in the following sense, that, I mean, real people, they will, sometimes they do mathematics, but, you know, at other moments they do other things. And they may fall asleep, they may lose interest, they may decide to quit the field. There are all kinds of reasons why constructions will not be completed or not be begun at all. Whereas Brouwer's interest is in, or it may be just that you do mathematics, but you forget what you have done before. All these things Brouwer says, he abstracts from, or he idealizes to a notion of a subject who does not forget, who does not die, who does not fall asleep, who has finite but otherwise unlimited memory. Because he says, what he's interested in is what can we construct in principle, because only then you're staying with the construction principles themselves, and you're not taking things which are, relatively speaking, contingent into account. So, for example, Brouwer's interested in a theory of mathematics in exactly the same way as Chomsky is interested in a theory of, in linguistics. Of a theory of a language capacity. So in Chomskyan terms, you could say that what Brouwer wants to arrive at is a theory of competence in making mathematical constructions, and not a theory of performance. And therefore, he says, therefore I will think of, ideal memory, we never die, it's all potentially infinite what we can do.
Is it not introducing a new ontology? Because we mentioned the problem of ontology, which is basic in this discussion.
No, because in some sense, no, because these idealizations that you make, they are highly controlled, in the sense that you are allowed. So the idea is you idealize from what you actually introspect, and what you actually have, what you actually observe by way of mental capacities that you have, and then you say, from these I will. I will take away certain limitations to them, but I will not introduce capacities that I do not even observe in myself in some unidealized form. So in Brouwer's case, this means that he says it's okay to think that we can construct any finite number, but he says we can certainly not construct out of separate elements non-denumerable collections, for example. Because he says, I do observe in myself the beginnings of constructing the finite numbers, but nothing like non-denumerable construction. So that's not going to be introduced. And then, so this will be the first. I'll get back to you right away. So this will be the first stage where you say, well, we speak of some idealized subject, but we will not admit any idealization. Right? They are controlled by what we introspect. And then the second stage is to say, in some sense, we are interested in the construction methods that are defined somehow, or that can be conceived of as really essential properties of a mind. You can think, in Husserlian terms, you could think of properties of the transcendental subject, right? So you could say, in Brouwer's case, he would say, with Husserl, by the way, so well, any mind, right, in virtue of being a mind, has time awareness. And then Brouwer says, aha, but out of the structure of time awareness, I can show you how you get mathematics, right? If you're willing to then add some idealizations, of course. But he says that's the construction material. Now, then if you think, well, what does it mean to be a mind? If by some philosophical analysis you arrive at the conclusion that to be a mind requires at least to have time awareness, then Brouwer can say, well, look, this means that any mind will have this time intuition out of which I then construct mathematics. So in that sense, he could say, and in fact this is what he does. He says, yes, it is true that we cannot communicate at the level of mind directly. We have to do this through language, which is imperfect, and we can always misunderstand each other and so on. Yet even so, to the extent that I recognize other minds, I will thereby recognize them as having this, this time awareness, and in principle capable of making the same constructions that I do. So in this sense, it is a notion of subjectivity, of course, which is at work, but it's not psychological or empirical subjectivity, but it's some essential notion. You're just wondering, well, what does it mean to be a subject? Out of that you get some properties, and then Brouwer says, no, well, out of these properties I can construct mathematics. Then by definition, any subject will be able to reconstruct in the same way. I mean, that's a strategy, right? Whether you can make it work or not is not a question, but this is a strategy.
Well, except that you admit that your awareness of time is potentially infinite.
Yeah, and
that's the main point.
Yeah, and it remains the main point for Brouwer too.
And we all know about the limitations, of course. And, that when you say we can construct in principle every number, but
every finite number. Yes.
Every finite number, agree. But it's not a question to go into non-linear variable or whatever. But the main problem is, which I mentioned already, which is the problem of translation. With the invention of the decimal notation, binary for that purpose. I mean, when you write something in decimal notation, you are not creating a number. You are just describing a certain set of operations which, in principle, could produce a number. Sure. But it's very easy if I tell you 1.0000, I'm just describing a set of operations which is, in principle, is well defined, but you cannot perform because of obvious limitations. So that's exactly what I mean. Potential. I mean, between the potential, between the actual infinity and the potential infinity, there is and of course what is truly finite. There are intermediate degrees. And,
oh, very much so. But of course, in the situation that you described, there are actually two observations to be made. The one which you actually make, namely, you say, well, I can write down this number, this decimal notation, and you know, in principle, it should be a number. But I know that no one will ever be able actually to construct this number.
If you
right?
Find a number as a, a sequence of strokes or
yes.
whatever.
But then, of course, the other observation to be made is, yet you do know somehow, apparently, that what I've written down here in this notation, in this system of notation, in principle defines a number. And then the question would be, well, how would you know that? And there's a perfect explanation for that according to Brouwer and similar people who think in a similar way. But of course, that comes down to, yes, you see that this notation, because of the because of the way the notation system works, you see that yeah, in principle, if I would not lose interest, drop that, or any other unwelcome thing, then at some point I would arrive at a construction of this number. If you wouldn't have that insight, then you would also not know that what you've just written down is in principle a number. That's just what it means to say that in principle it is a number.
So but there is always a gap between what...
And then the difference between empirical psychology and Brouwer's mathematics is that the empirical psychologist will be most interested in what we can actually do or not, and that Brouwer is most interested in what can be done in principle.
Okay, well that's it.
But they all agree on the phenomenon, right?
Okay. But a clear description. But there is a gap, I mean...
Oh, yeah, many, yes.
Well,
yes.
Just a question about the relationship between Intuitionism, in the way you described it, and computability. In a way, starting from a theory of mind, going to the construction of the continuum, I had the feeling that Intuitionism was a kind of version of computability with a theory of mind.
To a large extent it is, but not completely.
So the theory of mind is something like the theory of shared programs.
Yeah, to some extent, yes. I mean, the one caveat is that you can, and in fact Kripke showed this, you can define, based on this theory of the creating subject, you can define a function which intuitively is effectively computable, but which is not recursive.
Mm-hmm.
So some people think that's problematic, but... yeah.
Thank you very much.
Oh, thank you.